Our first question, what is torch.nn.Module? Torch.nn.Module is the base class for all neural network components in Pytorch. It's like the foundation of your AI house. Think of nn.Module as a Lego baseplate. Every neural network piece you build must inherit from this class. It automatically handles parameter tracking, GPU movement, and training modes. When you create any layer or model, you're essentially building on this foundation. Summary: Module is the essential foundation for all Pytorch networks. Our next question, how do you define a custom model in Pytorch? Create a class that inherits from nn.Module, define layers in init, and implement the forward method. Building a custom model is like writing a recipe. First, you list your ingredients, which are layers, in init, then you describe how to cook them together in forward. Pytorch handles all the complex backpropagation magic behind the scenes. Summary: inherit module, define layers, implement forward for custom models. Our next question, what's the difference between model.eval and model.train? Model.train enables training mode with active dropout and batch norm. Model.eval disables them for inference. Think of train as study mode where your model learns with randomness and adjusts statistics. Eval is exam mode where the model uses fixed knowledge without randomness. Always switch to eval before testing your model's performance. Summary: train mode learns with randomness, eval mode uses fixed. Our next question, what does nn.Sequential do? nn.Sequential chains layers together in order, like connecting train cars that data flows through sequentially. Sequential is Pytorch's assembly line. Data enters the first layer, gets processed, then automatically moves to the next layer, and so on. It's perfect for simple, straight-line architectures where you don't need complex branching or custom logic. Summary: Sequential creates an assembly line of connected neural layers. Our next question, what is the purpose of forward in a model class? Forward defines how data flows through your model. It's the recipe that transforms input into output. The forward method is your model's brain. It tells Pytorch exactly how to process data step by step. When you call model with input, Pytorch automatically calls forward. This is where you define the computation graph that enables automatic differentiation for backpropagation. Summary: forward method defines data flow and transformation through networks. Our next question, what are common activation functions in Pytorch? ReLU, sigmoid, tan, and softmax are the most common. Each adds nonlinearity to help networks learn complex patterns. Activation functions are like decision makers in your network. ReLU is the most popular. It's simple and prevents vanishing gradients. Sigmoid squashes values to 0 to 1, tan to -1 to 1, and softmax converts outputs to probabilities that sum to 1. Summary: activations add nonlinearity, enabling networks to learn complex patterns. Our next question, what is the use of nn parameter? Nn parameter tells Pytorch this tensor should be learned. It automatically gets added to model parameters and gradients. Think of nn parameter as a VIP pass for tensors. Regular tensors are just data, but parameter tensors are special. They get tracked by the model, included in optimizer updates, and moved to GPU automatically. Use them when you need learnable weights beyond standard layers. Summary: parameter makes tensors learnable and trackable by Pytorch. Our next question, how do you initialize model weights manually? Use torch.nn.Module or access weight and bias directly. Proper initialization can dramatically improve training. Weight initialization is like giving your model a good starting point. Poor initialization can lead to vanishing or exploding gradients or slow convergence. Xavier initialization maintains variance across layers, while He initialization works well with ReLU activations. Summary: proper weight initialization provides good training starting points. Our next question, what are hooks in Pytorch? Hooks are spy tools that let you peek inside your model during forward and backward passes without modifying the code. Hooks are like security cameras in your neural network. They watch what happens at specific layers and can capture intermediate values, gradients, or even modify them. Perfect for debugging, visualization, or extracting features from pre-trained models. Summary: Hooks spy on layers, capturing intermediate values for debugging. Our next question: how can you freeze layers in a neural network? Set requires _grad equals false for layer parameters. Frozen layers don't update during training, perfect for transfer learning. Freezing layers is like putting them in a time capsule. This is incredibly useful in transfer learning where you want to keep pre-trained features and only train the final layers. It saves computation and prevents destroying learned representations. Summary: freezing prevents layer updates, preserving learned transfer learning features. Our next question: what are the steps in training a model in Pytorch? Forward pass, calculate loss, zero gradients, backward pass, update parameters. It's the learning cycle. Training is like a feedback loop. You show the model data, measure how wrong it is, clean the slate, learn from mistakes, and improve. This cycle repeats until your model becomes smart. Summary: training cycles through forward, loss, zero, backward, update steps. Our next question: how do you define and use a loss function? Loss functions measure how wrong your model is. Use cross-entropy loss for classification, MSE loss for regression. Loss functions are your model's report card. They tell you how far off your predictions are from the truth. Cross-entropy loss is perfect for which category problems, while MSE loss works for how much problems. Lower loss means better performance. Summary: loss functions measure prediction errors, guiding model improvement. Our next question: explain the use of optimizers in Pytorch. Optimizers update model parameters based on gradients. They're the engines that drive learning in neural networks. Think of optimizers as smart coaches. They look at gradients and decide how to update weights. Different optimizers have different strategies. Some are conservative, others are aggressive, and some adapt their approach based on training history. Summary: optimizers intelligently update parameters, driving neural network learning processes. Our next question: what's the difference between SGD and Atom optimizers? SGD is simple and stable. Atom is adaptive and faster. SGD needs manual tuning. Atom adjusts learning rates automatically. SGD is like a steady walker, consistent but might need help with learning rate. Atom is like a smart runner. It speeds up on flat terrain and slows down on rough patches. Atom often converges faster, but SGD sometimes finds better final solutions. Summary: SGD is steady and stable. Atom adapts automatically. Our last question: what is the role of learning rate in training? Learning rate controls how big steps your model takes when learning. Too high equals chaos. Too low equals slow progress. Learning rate is like the gas pedal of your car. Press too hard and you'll overshoot your destination or crash. Too gentle and you'll reach your goal, but it will take forever. The sweet spot helps you converge efficiently to the best solution. Summary: learning rate controls training step size, affecting convergence speed.